Hello, my name is Jonah Carlisle, and this is Birdsong Rain Detection. So biologists at Georgia Tech want to collect birdsong from around the campus to get a measure for the amount of wildlife in the area. They can't realistically manually parse through all of the audio data in search of birdsong, so instead they have to develop automated systems to do the task for them. However, as with all automated systems, noise is a serious factor. As a result, we've been tasked with creating detection algorithms to search out this noise. The noise that I've chosen to detect is rain. The project really only has one major objective. We have to create a script that will take in an audio file or multiple audio files and produce a text file with the same name as that audio file that contains timestamps and labels that define whether rain was present in that section of audio. The main environment that I decided to use for the project was MATLAB. I chose MATLAB over Python because of its extensive debugging features as well as its many existing libraries. As far as the actual method for deciding whether an audio segment has rain or not, I decided to use a support vector machine due to the binary nature of the classification. We were given several different data sets of sound samples collected from around Georgia Tech campus. Some of these could prove useful for training our SVM, but some others could also become problems for testing it. For example, the Anderson-Serviceberry dataset has white noise that sounds alarmingly similar to rain. Even me, an actual human listening to the audio samples, couldn't tell if what I was listening to was white noise or rain. Some others, like Architecture West, have significant noise present, or what sounds like either a vent or a fan. Now, despite the usefulness of these sound clips, especially because they're from Georgia Tech itself, which is the target location for the use of this script, there likely isn't enough actual rain present in these clips to properly train our SVM. As a result, we need something more than the datasets that were just given to us. After searching for datasets online, I found the FSD Noisy 18K dataset. This is a dataset that was created by scraping the metadata and tags from freesound.org. It consists of 42 hours of audio with 20 different sound classes, rain included. However, the metadata and tags of freesound.org are user-submitted. This causes the dataset to be completely unreliable, hence its name, FSD Noisy. Therefore, we can do slightly better. I personally verified all 600 audio samples of rain from the FSD Noisy 18K dataset. Some of the most common cases of mislabeling were shakers, running water, overpowering noises such as thunder, windshield wipers, or clips with only thunder itself present in the clip. On top of throwing out these common cases, I also threw out samples in which I felt like the acoustics were too far from our use case, or in which I felt like the rain was too overpowered by other sounds within the sample. After manually verifying all 600 audio samples, around 258 valid rain samples were left. This will make up my rain present class for the SVM. As for the no rain class, I originally was just going to use the remaining part of the FSD Noisy 18K dataset. However, after implementing this, I quickly realized that this was a mistake. Too many of the clips within the FSD Noisy 18K dataset were just isolated sounds with no background noise to speak of. As a result, the acoustics were just too far from our use case, and the efficiency of the SVM was quite poor. Instead, I chose the EBB dataset to make up my no rain class. This was because the dataset was collected on campus, which will give it very similar acoustics and noise to our use case. Then, finally, 10 additional rain samples were collected from SoundJ.com in order to test the model against a dataset that wasn't used to train it. Now that we've determined our training data, the next thing to do is determine what features we want to extract from that data. In detection of rain and acoustic recordings of the environment, 5 different features were detailed as being particularly good at classifying rain. Those features were temporal entropy, spectral entropy, background noise, acoustic complexity index, and spectral cover. However, I didn't end up actually implementing all of these features. In my implementation, I only implemented temporal entropy, spectral entropy, and acoustic complexity index. My reasoning for only implementing these 3 features instead of all 5 simply comes down to availability. Within MATLAB itself, and the packages found within the package library, only spectral entropy was implemented out of all 5 features. As a result, I had to hand implement the other features. This was time-consuming and difficult, and as a result, I decided to stop once I found success with the features I had already implemented. With that said, onto the structure of the code itself. My code has 3 main functions for the user to interface with. Those are train SVM, which creates an SVM model, test model, which tests and rates the efficiency of the model, and detect rain, which creates a text file with timestamps and labels for when rain appears within an audio file. The train SVM function accepts 2 inputs and has 1 output. The first input is the path to the folder containing WAV files with rain in them. Train SVM first uses getWAV names to retrieve the name of each WAV file within each folder. Then it extracts the feature of each of these WAVs using the extract feature function. The features that are extracted using the extract feature function are concatenated and then ran through the fitcsvm function that is found within the machine learning toolbox. Then, finally, the trained SVM model is returned. Test model, like train SVM, loads and extracts the features from the WAVs in the exact same way. However, it must then load the SVM model from models.mat within the same folder. Once the feature vector and model have been obtained, each feature is ran through the predict method. The true positive, true negative, false positive, and false negative metrics are then recorded. Then, the accuracy metric is calculated and all 5 metrics are returned. The detect rain function uses getWAV names and extract features to create a feature vector in the same way as the previous 2 functions. However, it then creates a text file for every single WAV file that was originally imported. It then iterates through every single feature within that WAV file, and then uses the predict function to make an estimated guess as to whether rain is present within that segment or not. Then the timestamp and the outcome of that feature are recorded within the text file. This is repeated for every feature of every WAV file that is specified within the input arguments. The results of the model are pretty striking. There's an obvious outlier within this data. The model completely failed to accurately identify any of the WAV files located within the Architecture West dataset. This is likely because of the massive amount of noise from the fan or vent that is present in every single audio file within the dataset. While this may seem catastrophic at first, the poor signal-to-noise ratio of the rain versus the vent means that the classification of these samples as rain is secondary to dealing with the noise caused by the vent. That said, this is obviously a failure on the algorithm's part, and as a result, this should be taken into consideration. The other failure within the results is found within the Anderson dataset. The SVM model managed to properly classify 60% of the audio samples as not having any rain. While this may seem like mediocre results at first, the Anderson dataset across the board has white noise that sounds alarmingly similar to rain, even to a human. As a result, the fact that the algorithm managed to classify 60% as not having any rain can be seen as somewhat of a success. Past these 2 hiccups, the model performed fantastically. The Cherry, EBB, and SoundJ rain samples datasets barely had any misclassifications at all. As for the shortcomings of the models, it doesn't have enough measures in place to deal with overwhelming noise. It also can struggle to differentiate certain types of white noise from rain. First, I would increase the breadth of training data that I use, so that it contains more varied types of noise. Then, I would also implement the additional features that were discussed by Farouj in their paper. The main takeaway I had from the project was not to underestimate the effect that noise can have in data analysis. That said, I enjoyed the difficulty that came with trying to solve a problem that hadn't necessarily been solved yet.